Okay, for the second part, we're going to start to look at our electronegativity values, and we're going to determine what kind of bond we have by looking at those values. So we're going to start with sodium chloride. And when you look at your periodic table, sodium so if this is my periodic table and I see sodium symbol and it's number 11, you're going to see a number right here in the bottom left, and that's going to be the electronegativity value for sodium. So you can see that sodium has a number of 0.93. If you're not sure where that's at, stop the video, take a minute, look at your periodic table, and find this number for sodium on the lower left under its symbol. Okay, then we need to also find the number for chlorine. Chlorine has a higher electronegativity value, in part due to its smaller radius. It also has a more effective nuclear charge. What we're going to do is we're going to take the difference between these two numbers. So we're going to subtract them, and we're going to take the absolute value. What I usually do is just take the bigger number minus the smaller number. And so in this case, 3.16 minus 0.93 gives me 2.23. And what we determined in part 1 of the notes is that an ionic bond has a value between 1.7 and 3.3. And our value, the 2.23, falls within that range. So it's probably an ionic bond. Of course, there are exceptions, so the best way is just to still look for that metal. And because sodium is a metal, we know for sure that this is an ionic bond. Okay, the second type of bond is a polar covalent bond. And instead of a transfer of electrons to give us those full charges, we have a slight transfer of electrons. There's actually a transfer of electrons and a sharing of electrons occurring. So it's kind of like this tug of war. If you have, for instance, oxygen and hydrogen, and they're sharing a pair of electrons between them, one of these atoms will be pulling on the electrons more. In this case, it's oxygen because oxygen's number is 3.44, where hydrogen's is 2.2. And so even though they're sharing electrons, oxygen has more of those electrons on its side of the molecule. And that's because it has that higher electronegativity. So when you have a polar covalent bond, instead of having a full charge, we have a partial charge. For these types of bonds, the difference in electronegativity, delta N, is somewhere between 1.7 and 0.4. Okay, so if we look at our oxygen and hydrogen, let's rewrite this in a nice, neat way. If we have oxygen with hydrogen, and oxygen's number is 3.44, stop and make sure you look at your periodic table and find that number. So right here underneath the symbol, you should see this 3.44 number. And hydrogen is 2.2. So your delta En, you take the absolute value and subtract those two numbers. And so this gives me a value of 1.24. 1.24 falls within this range right here. And so that tells me that this is a polar covalent bond. and it's going to create partial charges. Okay, and then third type of bond. Now notice that polar was a type of covalent. Go back and look that again. Polar is a type of covalent. And then you also have non-polar covalent, where polar covalent has partial charges and you have this part sharing, part transfer. Non-polar is mostly sharing, and it leads to what we say is no charge. Okay, there might be some slight transfer, and so you could say that there's a minimal charge, but for the most part, we're just going to say it's no charge. Okay, these types of bonds have an electronegativity difference of somewhere between 0 and up to 0.4. So 0.39999 repeating. Carbon-hydrogen is an example of a nonpolar bond. Carbon has an electronegativity of 2.55. Hydrogen is 2.2. So we can subtract that and get 0.35. 0.35 falls in this range between 0 and 0.3999. And so that tells me that this is a nonpolar covalent bond. And then we also have bonds that we say are purely covalent. And that's when we have electrons that are shared equally. And so that means that we don't have one atom pulling more than another. An example of that would be Cl2 in your Cl2 molecule. Okay, so if we have these two chlorine atoms, and if they both have an electronegativity number of 3.16, you don't have one that's going to be pulling on the shared pair of electrons more than the other. And so the difference between these two values will be 0. So that's purely covalent. All Brinkelhoff diatomic elements are obviously going to be purely covalent. And then a nice easy way to look at all of this is to draw a figure. If your delta N, difference in electronegativity, falls between 0 and up to, but not including 0.4, so if it falls within this range right here, then we say this is a nonpolar covalent bond. If it's above 0.4, it's polar covalent. Or it could be ionic. Okay, it really just depends on if it has a metal. So if it has a metal, it's an ionic bond. If it's above this and it doesn't have a metal, then it's a polar covalent bond. There's a little bit of overlap over here, so it could have a metal and still be polar covalent. In terms of delta N, it could have